In Module 5, we're going to be discussing dimensional analysis and similarity. And this is Chapter 5 in your textbook. Now, dimensional analysis and similarity discusses essentially the planning, presentation, and interpretation of experimental data. So previously we had looked at analytical techniques to solving problems and mathematical techniques to solving problems. Now we're going to be studying how experimental data can be used, presented, and interpreted. So I'm going to write down that it discusses planning, presentation, and interpretation of experimental data. And we're going to see that through this chapter, we're going to be able to make a lot of simplifications to experimental problems and see how experimental data can be best achieved, essentially. So in this chapter, we're going to be looking at something where data is usually said to be best presented in dimensional form. So we can say that data is best presented in dimensional form. Dimensionless form. And in fluid mechanics, these dimensions, we're going to break down our dimensions into the simplest 4 dimensions we can think of. So the 4 dimensions that we're going to be using in fluid mechanics are the following. We're going to be using 4 basic dimensions. And those 4 basic dimensions are L, theta, M, and T. So what do all these dimensions stand for? So L stands for length, theta stands for temperature, M stands for mass, and finally T stands for time. Okay, so do not mix up temperature and time, but we have both in the term. Now, we usually call this an MLT theta system. And we can also use, as an alternative to mass, we can also use an FLT theta system, where instead of mass, we would have a force in newtons as our 4 basic dimension. Okay, so these are 4 basic dimensions in fluid mechanics. Now let's take an example and try to understand what's happening. So let's take an example and how we can apply this to a system and understand what's happening and how we can apply it to an experiment. So suppose that we know a force on a body and this body shape is immersed in a stream of fluid. Okay, so we're going to suppose we know a force on a body shape, so on a certain body shape, immersed in a stream of fluid. okay? And we can say that the force of that system, so the force is going to depend on a few different parameters, right? The force on the body shape immersed in a stream of fluid. So let's say we have a stream of fluid going this way. Okay, we have just a stream of fluid, and then we have a body shape, and there's a certain force on the body shape. Now, this force on the body shape, we can say it depends on a few different parameters. So we can say that this force is going to depend on body length, so the length of the body, okay, or the size of the body. So we're going to write L in brackets. It depends on the stream velocity. Okay, if the stream velocity changes, you're going to get a different force. It also depends on density or the fluid density. Not really the body density, but more the fluid density because we're looking at the force on the body. And also the fluid viscosity. And if you remember, viscosity is mu. And so we can say that this force can be written as a function of all these parameters that are changing. So these parameters that are changing are length, velocity, density, and viscosity of the fluid. Okay, so now we have a function for force with the four variables that allow us to change the force. So if we change the length of our system, we're going to have a different force. If we change the velocity of our fluid, it's going to have a different force, etc., etc., etc. Now, this becomes a very complicated equation, right? We have four terms. How do we solve this problem? We cannot solve this with equations. Okay, a function of four parameters in terms of force is going to be very complicated to have one equation to solve the whole problem. It's usually too complicated to solve with equations to find the exact force on a system. So what we need to do is we actually need an experimental function instead. We need an experimental function that will allow us to find the relation between force and other parameters. So what we can do is we can run some experiments to find the relation between force and length, the relation between force and velocity, the relation between force and density, and the relation between force and viscosity. And what we can do is, for example, so what is an experimental function? An experimental function is just can be thought of as a curve. So this experimental function can also be thought as a curve. Okay, it's just a curve relating two parameters. So we can do a graph, for example, of force times the length, and we're going to try a different length. We're going to see what the force is. So we're going to have some data points like this, and we're going to be able to curve fit through the data points and get a straight relation between the two. And we get that force is equal to 1.5 L, for example. Okay, so force is related by 1.5 times the length. So we can say that to find the effect of L on F, you need, for example, 10 lengths to run an experiment. So in order to find the effect of length on force, you need 10 lengths to run an experiment. And in order to run these 10 lengths, you also need to keep all other things constant. Okay, so remember our force is a function of length, velocity, density, and viscosity. We need to keep all others constant while we do the changes in length to find the relation between force and length. And then if we need to come up with an equation for all the other systems, we then need to do for each length that we do, if we want to have the relation at each length and come up with an equation for velocity, density, and variation in viscosity, we need to test at each length, we need to test 10 velocities, 10 densities, and 10 viscosities. So that means that we need to do 10,000 experiments to find an experimental function for force. Seems like a bit of a tedious problem to do, right? Well, with dimensional analysis, we can actually reduce this amount of experiments to a lot less experiments, essentially. So we can say that with dimensional analysis, we can reduce the amount of experiments drastically. And how we're going to do this is we're going to actually reduce our equation and change our function to have one term as a function of another. So we started with force is equal to a function of length times velocity times density times mu. And we can reduce it to the following. So what if we did force divided by density times velocity squared times length squared? If we make it essentially non-dimensional, we can say that now our system is going to be a function g, so a different function, times a function of density, velocity times length over mu. Okay, and right now I'm just writing it down. This is something that we can actually do. Okay, it's not something that doesn't work. It's an actual equation. For now, I'm just going to write it down, but we're going to derive how to do that in an example a little bit later. So what we've done here is we've made it a dimensionless force coefficient. So we've made it a dimensionless force coefficient on the left. And if we make it a dimensionless force coefficient on the right side, we can now create a dimensionless number that will relate all of the velocity, length, density, and viscosity together. And now we have a coefficient of force is equal to a function of Reynolds. Okay, and this is because this is called the dimensionless Reynolds number, which you might have heard of before, but if you haven't, it's fine. So the dimensionless Reynolds number is written as RE. And this function now is found from experiment. So now we can devise, for example, 10 experiments. So now we can do 10 experiments relating our coefficient of force and our Reynolds number, or our term rho v L over mu. So if we change rho v L over mu, for example, we can change it 10 times and we'll get a relation between the force coefficient and the Reynolds number. So we can do 10 experiments to get a relation between all the terms. And that's great, because if we do 10 experiments, we save on doing 10,000 experiments. So if we look, if we have our sphere in a path of flow, what is going to be the cheapest way to run 10 experiments with 10 different Reynolds numbers to find 10 different coefficient of forces and then plot them on a graph? So you would plot them on a CF times Reynolds number graph, and you would get a relation, for example. And then from Reynolds number, you can find, if you know your density, you know your velocity, you know your length, and you know your viscosity, which we already said, we can then find our force from that. So from our simple function, we can find our force from the coefficient of force, which was written earlier. And obviously, to change the Reynolds number, the cheapest way to change it cheapest way to change Reynolds is to change the velocity of the flow, right? If we can change, if we have the choice between changing the density of the air or the density of the fluid that the flow is in, or changing the length of the actual system that's being tested, or changing the viscosity of the fluid, the easiest way is to change the velocity of the fluid, and we can get 10 different Reynolds numbers. Okay, so very, very powerful technique that we're going to be talking about in a little bit more detail now. So another example of a dimensionless parameter that we use a lot in addition to Reynolds number. So Reynolds number is one that we're going to be using a lot, but there's another one too that should be familiar as well. So we can say that at high speed gas flows, so this is only for gases usually, F, the force, usually depends on a very simple relation, which is called the Mach number. And what the Mach number is ma is equal to the velocity over little a, which is the speed of sound. This is the speed of sound in our textbook. Okay, it's a, little a. So with Mach number, we can actually relate our force with Mach number, and it makes it very easy to solve our problems and to non-dimensionalize the problems, because velocity over speed of sound is a dimensionless parameter. If we have different velocities, we can now normalize our force in relation to the Mach number. And one last number that we're going to be using as well is the Froude number. So in free surface flows, so like a boat floating on water, okay, flows which have a free surface. So usually we're interested in like ship drag, okay, the drag that a ship has in the water. We can say that the coefficient of force depends on the Froude number, which is called F little r. It's actually F lowercase r is equal to V squared over G times L. Okay, and through your study problems in this section, you'll be able to study all these different parameters, and we're going to be doing an example problem as well. So those are the three main ones we're going to use. So Reynolds, Mach, and Froude. Now, some of the other benefits. So some of the other benefits that we get from using dimensionless parameters is that we can provide scaling laws that convert data for small scale to large scale. So the other benefits of using dimensionless parameters is that we can scale to convert data from small scale experiments on cheap models to big prototypes. So for example, if we want to test the wing of a Boeing 747, we don't actually need to test the wing of a Boeing 747 in a wind tunnel. We can make a small scale model, and then through dimensionless analysis, we can say that if the Reynolds is matched together, or if the parameters are put together so that they're equal, then we can scale it up. So for example, if we take our fact that our coefficient of force is equal to a function g of Reynolds number, and we know that the force is equal to a function of length times velocity times density and viscosity, so not multiplied, but a function of all these different ones, we can say that if we have the same shape or the same design and the same shape, we can say that if Reynolds of our small scale model, for example, is equal to the Reynolds of our prototype, which is the case if you're doing the same type of analysis, okay? So if you make a model that's 4 times as small as a prototype, okay, if you make a little model of a prototype, for example, a 747 wing, and you divide it by 4 in size, you can actually say that if the Reynolds are the same, the relation between the force and all the parameters is also going to be exactly the same. That's something you can do. And so you can say that from Reynolds, you can say that if Reynolds of model is equal to Reynolds of prototype, that means that the coefficient of friction, of force, of the model, and I'll put M for model, is equal to CF, so coefficient of force of the prototype. And so we have, if we remember how we wrote our equation earlier, and we'll derive it later on, but for now we're just going to assume that that's the equation, we can say that F over rho times V times V squared L squared for the model is equal to force over rho times V squared L squared for the prototype. And that means that we can rewrite the equation as trying to figure out what the equation would mean in terms of force. So if we rearrange this equation here and we put the forces on one side, we would be left with force of the prototype, so the actual force you feel on a prototype on a real, for example, 747 wing, over the force of the model is going to now be equal to the density of the prototype over the density of the model, multiplied by V of the prototype over V of the model squared, multiplied by the length of the prototype over the length of the model squared. And we can say that this equation is only valid, okay, we can only use this equation if Reynolds of model is equal to Reynolds of prototype. So we can find the relation between our force of prototype and our force of model based on the Reynolds relation that we developed. So we can also say that if that is only valid with Reynolds of model is equal to Reynolds of prototype, we can write the equation for Reynolds of model and Reynolds of prototype. It's rho m Vm Lm over mu m is equal to rho p Vp Lp over mu p. Okay, and what is the parameter that changes between a model and a prototype? Well, the parameter that changes between a model and a prototype is this parameter here. So usually Lm is going to be equal to, for example, Lp over 4. Let's say it's a quarter of the size. So if it's a quarter of the size and we need to have a correct experiment for modeling how the prototype works, we now need to make Reynolds of model equal to Reynolds of prototype. So how can we do that? Well, we can play with the viscosity, we can play with the density. The easiest way to solve for that is to say, okay, then if we make Vm is equal to 4 times Vp, this would solve our problem. Okay, so our model is 4 times as small as our prototype, but if we use 4 times the velocity, we satisfy this equation. We satisfy this equation by doing that. So essentially, when you're testing a smaller model in a wind tunnel and you want to satisfy Reynolds dimensionless parameter, you need to increase the speed by the amount that you reduce the size of your model. Or you can change the density of your fluid, or you can change the viscosity of your fluid. Those are other ways of doing it as well. This concludes the first video in our module, and we'll be back in part 2 to discuss the Buckingham Pi theorem and how we can go from dimensional parameters to dimensionless parameters.